Lesson 7, Applications of Exponential Functions. Our goal in this lesson will be to look at where exponential functions can be applied in everyday life. We're going to specifically look at problems involving what are called exponential growth as well as exponential decay. This has to do with the fact that certain quantities over time increase or decrease in size, but they do so by some factor. For example, consider a colony of bacteria. They double in size approximately every 20 minutes. I posted a video on Moodle. It should be underneath the lesson. Please take a look because this will really show you what exponential growth means. But I'll just discuss a quick example. Let's say you start off with 2 bacterial cells, then they double to 4, then doubles to 8, 16, 32, 64, 128, 256. The point is, you keep doubling how much you had, so the number of cells will increase very quickly. Notice this is a much bigger increase than, say, something going at a linear rate, where you keep adding the same amount each time. As another example, many of you are probably looking to get your first car pretty soon as you get your G1 licenses, but cars depreciate, meaning they lose their value. The average value of a car probably loses about 30% of its initial value every year that it's owned. That makes new cars not great investments. We'll talk about this more later. Let's start this lesson off with exponential growth. Below is the general equation representing exponential growth. Let's go over what each of the different variables represent. First of all, a of t, this is meant to represent the amount of something at time t. So in this case, a is the dependent variable, the amount, and t is the time, which is the independent variable. A sub 0, often read as a naught, or a with a subscript of 0, represents the initial value. In most cases, the initial value will be taken to be at time t equals 0. Think of it like you start a stopwatch at t equals 0, and however much you had at that time would be your initial amount. G represents the growth rate. To use it in the formula above, it must be expressed as a decimal. This is very important. Oftentimes it will be given to you as a percentage, but you have to convert it to a decimal. Little t is the time, and we have a new variable here. This kind of looks like a funny t. I'll just highlight it right here. And I'll make a note, this is actually the Greek letter tau. I'll spell it out. Tau represents the time it takes something to grow or decay. For instance, if a colony of bacteria doubles in size every 30 minutes, then tau would be 30 because this is the time it takes that colony to double in size. And I want to make one important note, but in order to use this formula correctly, t and tau must be in the same units. That could mean both in hours, both in minutes, both in seconds, etc. Okay, let's try out an example. This will be a relevant question to everyone. The cost of university tuition has been increasing at a rate of about 2.7% every year. The 2.7%, that would be the growth rate. Let's make a note. Don't forget to convert it to a decimal, so divide by 100 to get 0.027. One other thing, it's increasing at this rate every year. That means that for every year that goes by, the tuition is 2.7% higher than what it was the year before. So in this case, tau, the growth rate, is every 1 year. And we're being told that the current cost of tuition is $8,000, so that would be the A0, the initial amount. So let's begin by writing an exponential function. I'll start off by writing the general function. So the exponent has a fraction, t over tau. And now you can just plug in the numbers from the question. And if possible, simplify it a bit. So I would add the 1 and 0.027 inside of the brackets. And as for the exponent, anything divided by 1 is just itself. So final answer. And that's going to be our simplified exponential function representing the cost of tuition as a function of time. Let's put it to use. What will be the cost of tuition in 5 years? So the 5 years here, this represents t. In other words, how much time has passed? A common area of confusion is for students to mix up the two different times. Little t represents the amount of time that you would like to know how much of a quantity you have. In this case, we want to know the cost of tuition in 5 years. But tau is the growth rate. That tells you how long it takes for the quantity of interest to increase by a certain percentage. In this case, it's 1 year because the cost of tuition goes up by 2.7% for every year. So everyone, we just simply plug in t equals 5 into the function. And I'd like to make a note here. I'm allowed to just plug it in because t and tau had the same units. They're both expressed in years. That's very important. You always have to make sure the two units match. So this is something you can evaluate on your calculator. Please don't forget BEDMAS. So you're going to have to do exponents before multiplication. So on your calculator, take the base of 1.027, raise it to the exponent 5. That's going to give you a number, and then multiply that number by 8,000, and you should get an amount of approximately $9,139.92. For all money-related questions, please round to 2 decimal places. And there you go. If tuition keeps increasing by 2.7%, it'll go from $8,000 to almost $9,000 over the course of 5 years. Okay, please write a therefore statement to keep up with good communication, and we'll move on. Let's try another one. Imagine a bank offers you an account in which your investment will double every 6 months. First off, good luck finding a bank that will allow your investment to double every 6 months. That's a very good rate of return, and unfortunately is highly, highly unlikely. So let's break this down. If something doubles, you have twice as much as what you've had before. The common mistake is to think that when something doubles, the growth rate is 200%. The growth rate is actually 100%, or 1.0 as a decimal. And the reason for this is, imagine if you had $100. Here, let's just make a side note below. Let's say you had $100 and your money increased to $150. So how much money did you gain? You gained $50. $50 is 50% of 100. So in this case, the growth rate is 50% because it increased by 50% of what it was. Let's say your money doubled though. So you had $100 and it magically becomes $200. So your money increased in this case by $100. But $100 is 100% of the initial $100. So when something doubles, the growth rate is 100%. If you found that helpful, maybe write it down on a separate sheet of paper. I'm going to erase it now in order to make room for the example. Okay, let's continue. So we're doubling every 6 months. So the 6 months here represents the tau, the doubling time. I'm going to keep it in units of months for now. Let's continue reading the question. We invest $200 into the account today. So that would be our A0, the initial amount. And the question is, how much money will you have in 2 years? So that 2 years represents the time. All right, so first things first, notice that t and tau don't have the same units. So we have two options here. Either we convert the 6 months into years, or we convert the 2 years into months. I personally prefer to go from a bigger unit to a smaller unit. So 2 years is equivalent to 24 months. All right, so let's set up our exponential growth equation. A of t equals A0 multiplied by 1 plus g to the exponent of t divided by tau. We'll do this in steps. Please substitute your values. So the A0 is $200. That's how much money we've started with. The growth rate is 100% or 1. I'm going to leave little t as a variable for now, but for tau, I'll plug in the 6 months. All right, let's simplify this. So it's 200 multiplied by 2 to the exponent of t over 6. And I'd recommend that you always set up the equation fully first. After you've done that, then it's a good idea to plug in the t. So we want to find the amount, or in other words, the money in 2 years. So that would be 24 months later. So I'm going to plug in t equals 24. If you look at the exponents, t and tau are in the same unit, so we're good. And now we can continue simplifying this. So this is 200 multiplied by 2 to the exponent 4, because 24 over 6 is 4. Don't forget BEDMAS, please. You have to do exponents before multiplication. So it's 200 multiplied by 2 to the exponent 4. That's 2 times 2 times 2 times 2, or 16. And lastly, you can multiply 200 by 16 to get 3,200. So just think about that. A $200 investment becomes $3,200, over the course of 2 years. Once again, that's a very unrealistic expectation. Probably a realistic good investment is about 7% per year. All right, let's write a therefore statement. And we are done. Moving on. All right, here's another example of exponential growth. So Bob has an ant colony. The population doubles every month. So as we discussed before, when something doubles, that's a growth rate of 100% or 1. It's doing so every month, so that's the tau. Tau is every 1 month. We start off with 100 ants, so that would be our A0, the initial amount. And I just want to mention here, you can use exponential growth to model anything. It can look at the number of ants, it can look at the amount of money, it can look at the cost of tuition. All of these questions follow the same general format, and you can apply it to any situation. All right, first question, how long will it take until the colony reaches a population of 3,200 ants? So this one's a little different. It's giving us the final population. So that would be the final amount, which is A as a function of t. Let's always start off by setting up our equation. So A of t equals A naught or A0 multiplied by 1 plus g to the exponent of t divided by tau. So before we plug in numbers, let's ask ourselves what we're being asked to find here. We want to know how long it will take for the population to reach 3,200. So basically we're trying to solve for t now. And t is in the exponent, so I'll show you how we solve it when it's in the exponent. On the left side, a of t, we'll replace that with 3,200. A0, replace it with 100. In the brackets, you have 1 plus g to the exponent of t over tau. So if I'm keeping my tau in months, that means the time I find will be in months as well. Let's clean this up a bit. So 3,200 equals 100 multiplied by 2 to the exponent t. Recall, when you're solving equations, you use BEDMAS in reverse. So let's begin by dividing both sides by 100. You have to undo multiplication before exponents. 3,200 over 100 gives you 32. And now that equals 2 to the exponent t. So please listen up. This is the question we're trying to answer. 2 to what exponent is 32? One trick that you can do is to write 32 as a power of 2. In this case, 32 is equivalent to 2 to the exponent 5. Now look at your equation. You have the same base of 2 on both sides. Those are the same. So what has to be true in order for the left side of the equation to equal the right side? Well, the exponents, whatever they are, have to be the same. That's the only way for the left side to equal the right side. So therefore, we get that t equals 5. That means in 5 months, the ant colony will reach a population of 3,200. Okay, let's try another one that's slightly more challenging. This time we want to know how long it takes for the ant colony to reach a population of 10,000. So once again, that's the A of t, the final amount. We're using the exact same equation from part A. It's just the left side equals 10,000 instead of 3,200, so I'll write that out. All right, very similar to before. Divide both sides by 100. Ten thousand divided by 100 is 100. So now the question we're trying to ask is 2 to what exponent equals 100? Now unfortunately, you can't write 100 as a power of 2. So you have to use something here called guess and check. This is usually a method that most math teachers don't approve of, but in this course it's fine. I just want to say in grade 12, you're going to learn a way to do this without guess and check, but for now, that'll be sufficient. But I want to save you some time. Instead of just randomly punching numbers on your calculator, let's make a few educated guesses. So what two numbers, or I should say, what two powers of 2 is 100 in between? For example, notice that 2 to the exponent 6 is equal to 64, and 2 to the exponent 7 is equal to 128. So that means t has to be somewhere between 6 and 7 because the number 100 is somewhere between 64 and 128. So I'm writing this out kind of like what we did for domain and range back in Unit 2. Reading this left to right, I'm saying 6 has to be less than t and t has to be less than 7. In other words, t is somewhere between 6 and 7. So you've narrowed it down. At this point, please go ahead and use guess and check on your calculator. If you're wondering how accurate you have to be, I'd say probably 1 decimal place is enough. If you want to try 2 decimal places, please go ahead. So this would be a good time to pause the video. Let's see how close you can get. Please don't nitpick about being super exact. You're never going to get it exact. Once again, I'd say 1 decimal place is okay, maybe 2. So go ahead, try it out. All right, are you ready? So I think you should have got approximately 6.65. That's probably as close as we're going to get to 100. So therefore, the ant colony will reach 10,000 by about 6.65 months later. Oh yes, one more thing I need to mention. Because our tau was in units of months, that means t is also in months. All right, and we're done half the lesson. That was exponential growth. Let's move on to exponential decay. Exponential decay is sort of like the opposite of growth. Rather than something increasing with time, it's now decreasing with time. Below you'll find the general equation representing exponential decay. Notice it looks very similar to exponential growth. So once again, A of t is the amount of the quantity at time t. A0 is the initial value that usually occurs at t equals 0. Instead of 1 plus g in the brackets, we have 1 take away d. D is what's called the decay rate. This has to be expressed as a decimal as well, very important. Little t once again is the time, and tau is the decay time in this case. I'll make another note, t and tau must be in the same units. Okay, let's put this to practice. So in example 4, we're told that the population of a small town was 8,400 people in the year 2005. So this is how many people we're starting with. That's your A0. And then due to poor job prospects, the population is decreasing at a rate of 3% each year. So 3% represents the decay rate, or 0.03. And because this is happening every year, that means tau is 1 year. One more thing I want to mention, this was the population in the year 2005. So 2005 is like t equals 0. What I mean is pretend this is the year that you start your stopwatch, and we're going to be measuring time relative to the year 2005. This will be important in part B. So as always, let's create our function. And simplify. Okay, there you go. So with that being said, we want to determine the population in the year 2013. So this is important now. You don't just simply substitute 2013 in the equation. 2013 has occurred 8 years after 2005. So we're going to plug in t equals 8 years. This is what I meant by starting the stopwatch in the year 2005. So we plug in 8 for t. This is a job for your calculator once again. So don't forget to use BEDMAS. You're going to have to take the base of 0.97, raise it to the exponent 8, and then multiply that number by 8,400. Doing so, you should get approximately 6,583. Because we're dealing with number of people, please round to a whole number. All right, everyone, write yourself a therefore statement, and we're done. All right, a car example. So imagine you buy a new car for $24,000, and we're told it loses about 18% of its value each year. That's actually a pretty realistic number. Like I said in the introduction to the video, new cars lose their value relatively quickly. So 24,000 is the initial cost of the car, A0. 18% is the decay rate. And it loses that value every year, so tau is 1 year, the time it takes it to lose 18% of its value. We want to determine the value of the car after 30 months. So that's t. Notice that t and tau don't have the same units. So once again, you're welcome to convert years to months or either months to years. Personally, I like to go from a bigger unit to a smaller unit, but it doesn't really matter. So tau, instead of 1 year, I'm going to write that as 12 months. All right, let's set up our equation. Simplify and then evaluate. All right, evaluate when t equals 30 months. I'm going to simplify the exponent. 30 over 12 is 2.5. And once again, this is a job for your calculator. So take your base of 0.82, raise it to the exponent of 2.5, and then that number multiply by 24,000. You should get a value of approximately $14,613.22. Because we're dealing with money, please round to 2 decimal places. So consider that your brand new car lost about $10,000 over the course of 30 months or about 2.5 years. All right, last example. This is a chemistry related example. Fluorine 20, so that would be an isotope of the element fluorine from the periodic table, has a half-life of 10 seconds. Half-life refers to the time it takes something to lose half of its original amount. It's sort of like doubling, but in reverse. So we have a container that has 500 cubic centimeters of the isotope. That's our initial amount. And we want to know how much remains after 120 seconds. So that's T. Now let's go back to the first sentence. Because the half-life is every 10 seconds, 10 seconds represents your tau. But the thing for half-life, because it keeps losing half of what it had, the decay rate is 50%. All right, so let's set up our equation. And simplify. All right, so that's your simplified exponential function. And now we evaluate it when t equals 120 seconds. So plug in 120 for t. I like to simplify the exponent first. $120 divided by 10 is 12. And once again, a job for your calculator. So take your base of 0.5, raise it to the exponent 12, and multiply that number by 500. You should get approximately 0.12. I didn't specify how many decimal places to round the final answer to, so I'm not that picky for these things, but I think 2 decimal places is more than enough. So please write yourself a therefore statement and we're done. Okay everyone, and that is officially the last lesson of Unit 4. Here's some recommended homework from the textbook. Please try it out, and remember, if anything is unclear, never hesitate to reach out or let me know. Thanks everyone, I'll see you in the next one.